Find the area of one petal of r equals 4 cosine of 2 theta. So very similar to the previous example, except this one has cosine in it. Cosine. All right? So let's go ahead and sketch it out. Typically, we always start with 0, right? So when theta is 0, what is the radius? Cosine of 2 times 0 is cosine of 0. Cosine of 0 is 1. 1 times 4 is 4. So we start over here at 4, and then because it's 2 theta, if we start picking random values of theta that are comfortable for us from the unit circle, we're going to have to double them. So if you realize you start at 4, unlike sine that started at the pole, this one starts at 4, and it's going to come in like that and hit the pole right there. So in this case, if you could find the very first polar 0 and integrate from 0 to that first polar 0, that is what fraction of one petal? That is half, okay? So this is where symmetry is nice, because when you're integrating by hand, it's nice to have 0 as an interval of integration, all right? So how do we find polar zeros? Set r equal to 0. So we got 4 cosine of 2 theta. You set it equal to 0. You divide through by 4, and you still get 0. And now you want to know where are the first, at least get 2. Where are the first 2 angles where cosine is 0? Pi halves and 3 pi halves. Good. Now those are not equal to theta. Those are both equal to 2 theta. So if you solve those for theta, then you get theta equals half of pi halves, which is pi fourths, and 3 pi fourths. So the first polar 0 must be at pi fourths. So if you integrate then, the area is going to be 2 times, because I'm just going to find this half of it, the integral from, 1/2, my bad, the formula is 1/2, the integral from 0 to pi fourths of r squared d theta. And of course, our r is 4 cosine of 2 theta. And there's the answer. Now, if you didn't want to use symmetry, of course, you could do a couple of things. If you know the first polar 0 is at pi fourths, then by symmetry, you could back up to negative pi fourths, right? So you could just go from negative pi fourths to pi fourths. Could you also just go from pi fourths to 3 pi fourths? You could, actually. You're not going to get a closed loop. If you do that, you're going to get this right here. But you're going to get that half, and you're going to get this half, and 2 halves do, in fact, make a whole. So it also works that way. But again, I like the symmetry aspect here, so let's simplify this. If I combine the 2 and the 1/2, because I'm doubling it because of the symmetry, that becomes a 1. But then the 4 is squared, right? So that becomes a 16. So the integral from 0 to pi fourths with the 16 out front of cosine squared 2 theta d theta is probably the most common integral that you'll see in terms of like a multiple choice answer. But if that's not there, just kind of look at the other answer choices. Again, you could go from pi fourths to 3 pi fourths. You could go from negative pi fourths to pi fourths, in which case if you do that, you're not going to have the 2 out there to double it, so you'll have still the 1/2, and then the 4 squared would be a 16, so you might have an 8 out front on a different interval. So different ways to set it up based on the coterminal nature. Of course, if you were going to integrate that by hand, power reducing identity, otherwise go to the calculator and get the decimal equivalent. So I'm not going to do that. Any questions on number 3? All right, number 4. Now it's getting a little more interesting. Find the area inside the loop of r squared equals 4 cosine of 2 theta. What's interesting about this is it's equal to r squared and not r. So if you were to graph this, you would probably want to solve it for r. And remember, it doesn't really matter if it's plus or minus, because it'll still trace out just kind of in the opposite fashion if it's a negative. So are there values of r for which this thing is undefined? Possibly so. Now, if it were just r equals 4 cosine of 2 theta, what would 4 cosine of 2 theta graph as? If it were just equal to r. It would graph as a rose, right? It would be a 4-petal rose curve. And it would trace out once from 0 to 2 pi, right? It would take twice as long. We could do this one by hand, but I'm not going to. I want to show you what it looks like in the polar graph. Because like a rectangular, you have to solve it for r in order to sketch it in polar mode, as you would for rectangular mode. 4 cosine of 2 theta. And if I hit zoom 6, let's see what my window is. I'm going to slow it down. I want you to see how it's graphing. So if I change this to like 0.005, that might slow it down enough. All right, so watch how it traces out. We're expecting a 4-petal rose curve, square root of it, though. Okay, so there's the first, and now it's disappeared, and then it finishes up. You see that? So it started, and then it went through the origin, and I don't know if you noticed this, but as it was tracing down here on the negative x-axis, or on the negative y-axis, it wasn't showing it at all, but it was still graphing it. And then it picks up at the pole and graphs this on the negative x-axis, and then it was coming up here, and it didn't sketch anything on the positive y-axis, but then it picked back up and finished the bottom half. The reason it's doing that is as it rotates up here to pi halves, the radius is going to be negative. And of course, you then end up with a negative under the radical. And what happens when you have a negative under the radical? You get imaginary radii, okay? So what this actually gives you is it gives you a 4-petal rose curve, but 2 of the branches from the graph, the one that's down here on the negative y-axis and one on the positive y-axis, they're imaginary. So you only see 2 of the 4 petals. And this right here is actually, it has a different name. It's not an imaginary 4-petal rose curve. We call this a, anyone know? Yeah, it's an infinity symbol. I'm going to show the imaginaries as dotted lines. This is called a, not that. That's called cool. This is called a lemniscate, and it looks like a figure 8. So lemniscate, figure 8, lemniscate. It is the infinity symbol. The infinity symbol is probably the most famous lemniscate. But again, it's a 4-petal rose curve with 2 imaginary petals. So let's go ahead and find the area inside one of the loops. Inside one of the loops. If you were to figure out where it started, let's do that, because that's kind of important. In order to figure out your interval of integration, you kind of need to figure out where it starts. So if we point due east, which is when theta is 0, if I plug in a 0 up there, I get cosine of 0 is 1. I get the square root of 4, which is 2. So it starts right there, and it's going to hit the first polar 0. So I can do pretty much the exact same thing. I don't want to draw lines like that. I can do the exact same thing I did previously. I want to draw lines like this if I'm going to draw lines, draw little radial lines. So if I can integrate from theta to the first polar 0, I can avoid the whole imaginary part altogether and just double it. So how am I going to figure out first polar 0? Plug in 0 for r. Good. Right. So if I set r equal to 0, now I'll square both sides. And of course, you end up with really the same thing as you would if you set r squared equal to 0. You divide through by 4, and you still get 0. Oops. So then 2 theta, cosine is equal to 0, just like on the previous one at pi halves and 3 pi halves. But we don't really need 2 of them if we know we're just looking for the first polar 0. The smallest positive 0 is pi halves, so if you solve that for theta, you get pi fourths. So here we go. The volume of this lemniscate by symmetry. Area, yeah, that's it, volume. Oh boy. Okay, thank you. Area is twice, and then the formula is 1/2 the integral from. I'm going to integrate from 0 to pi fourths r squared d theta. Now here's where you want to be kind of careful. If you square r, you're going to have to square the radical version. Notice that r is already squared. So it's just going to be 4 cosine of 2 theta. And you're not going to square it again. So it's one of the few where r is already squared. It's a lemniscate, r is squared. So this one actually is not that bad to integrate by hand. Let's go ahead and close this one out. This one is not going to require the power reducing identity. What are all my coefficients going to surmount to here? 4. So I have the 4 there. And then the inside function is 2 theta, which generates an unwanted 2. So I have a correction of a half. The antiderivative of cosine is sine. So then we evaluate it from 0 to pi fourths. And we end up with 2 beefy bracket sine of pi fourths times 2, which is pi halves, minus sine of 0 times 2, which is 0. And our final answer is 2. There you go. So what would be the area of the entire lemniscate? 4, right? You double it, because there's 2 of them. So there's a lot of, again, polar curves with fancy names. Lemniscate, just kind of a cool one because it is the infinity symbol. Yes? Well, it is pi fourths on the interval of integration, but it's 2 theta. Right, so when we plug it in, before we take the sign, we'll have to double the angle. So 2 pi fourths becomes pi halves, yeah. So a lot of trig in this section, as you can imagine. But no power reducing identity needed there. All right, so now they get a little bit more interesting. Because so far we've had just one curve, just parts of a curve, or the whole curve. But now we have 2 curves. So it's kind of like areas between 2 curves that we did in 6.2, but now they're polar curves. Find the area inside this guy, but outside that guy. All right. I guess we need to identify the region. So let's draw each of them. And here's where it could be helpful to know what the graph of each of them looks like. I'll graph this one in red. What can you tell me about 3 sine of theta from example 1? It starts at the pole, right? You can figure that out. And it has y-axis symmetry, and it traces out like that. Let me make it a little bit bigger. It has a diameter of 3, and remember, it traces out from 0 to pi. Okay, so that's what the first one looks like. The second one is going to end up being a what? Bless you. This one ends up being that dimpled limison. But again, if you're not sure, just pick your quadrantal angles. When you plug in a 0, sine of 0 is 0, you end up with 2. So you start there at 2. At pi halves, you end up with 2 minus 1, which is 1. So it's right there. Over at pi, you're back at 2 again. So this is at negative 2. And then down at 3 pi halves, you end up with negative 1. So that's where you're at the farthest away, which is 3. So you can see that it kind of opens down. So it comes in here, maybe dimples a little bit. Looks like that. And it has y-axis symmetry. Looks like a what? An acorn. Yeah, an acorn is a good description of it. Now here's the cool part about, first of all, about polar curves. In rectangular coordinates, anytime 2 graphs cross paths, they intersect, that is a true point of intersection because there's no speed component. These things do have a built-in speed component, right? If you think about the acorn, it traces out once from 0 to 2 pi, whereas the circle traces out just once from 0 to pi. So it's making 2 laps around its curve, while the acorn is making once around it. So on polar curves, just because 2 lines cross does not necessarily make it a true point of intersection, any more than if you saw 2 sets of tracks in the snow and you see the tracks cross, you're like, oh, there must have been a collision right there, right? Because they could have gotten to that point at what? Different times. That's kind of a neat aspect of polar area. So to be a true point of intersection, they have to be getting to the same place at the same time. Very interesting. All right, so let's go ahead and identify the region, and we'll see if that's even an issue. It has to be inside the red graph, but outside the acorn. So do you see that? That's going to be this region here. I want to find just that area. Everyone agree with that? Okay. So now what we need to do is come up with a plan to find it. Here's how we're going to find it. I am going to maybe use symmetry. Both of these have what type of symmetry? Y-axis symmetry. You want to treat these by drawing radial lines. That is, from the origin, if you draw a line to the first point of intersection, it looks like that. So if they do in fact intersect there, that's going to be my first angle. Theta equals, I'm going to call it alpha. Okay? At that angle. Now from there, if you draw your radial lines, if you start rotating, oops, you can generate most of the area by integrating the red curve, right? Probably up to where? Theta equals pi halves. That would be halfway around the circle. We know it makes one rotation in pi. So if I can find that from theta equals alpha, whatever it is, to pi halves, I could then double it. But would that give me just the blue region that I want? No, because notice I've gotten too much area. I've gotten this little piece down here that I want to get rid of. So now how can I get rid of that? I can subtract, right? I can come back now and I can integrate, as it turns out, on the same interval from alpha to pi halves, but this time I'm going to use the acorns curve as my boundary. See that? So if I find the green area and subtract the pink area, I'll be left with the blue area. We're tracing it out like windshield wipers, okay? So let's do this first. Let's find the points of intersection. And just like we would with rectangulars, we're going to set the equations equal to each other. So 3 sine of theta is going to equal 2 minus sine of theta. Set them equal to each other. Now, we'll get everything on one side. So we get 4 sine of theta equals 2. If we solve for sine of theta, we get 2/4, which is a half. And what we're interested in now, since it's kind of rotating off of 0, we want from the unit circle the first positive angle theta, where sine is equal to 1/2, which is what? Pi 6. Good. So now I found my theta. I'll just replace theta with pi 6. Okay, so let's go ahead and set it up. The area is going to equal, and I am using symmetry, right? It's just easier to do so. So I'm going to double it with a beefy bracket. And let's do the green one first. I'll color code it. It's 1/2 the integral from pi 6 to pi halves of r squared d theta. And of course, the green one uses the circle 3 sine of theta. And then inside there, I'm going to subtract now the pink radial lines that use the acorns curve. So it's another separate integral. 1/2 the integral from pi 6 to pi halves of r squared d theta. And that acorn curve is 2 minus sine of theta. Now this is the integral setup, and it'll work. And there are also other intervals that work. But if you notice here, because both of them are on the same interval of integration, they're both from pi 6 to pi halves, we can actually combine those two integrals into a single integrand. All right? So let's do that. A couple of things we could do. Let's go ahead and distribute the 2, shall we? That's the whole purpose of using symmetry. The 1/2 will go away. So then, with the 1/2 gone, I can just say it's pi 6 to pi halves. I'll put a beefy bracket here, and we might as well simplify as well. 3 sine of theta squared is 9 sine squared of theta, and then minus, I'll just leave this one factored because it's 2 terms. And then close that d theta. So this is very similar to what we did in 6.2, where we were trying to find the height of that representative rectangle. And remember, we practiced doing top minus bottom and right minus left. It's kind of the same thing here. We're doing the big curve squared minus the little curve squared. And they happen to be on the same interval, in this case from pi 6 to pi halves. The 1/2 is gone, of course, because we doubled it using symmetry. So if with the calculator now, you would just type that in and get a 3 decimal equivalent. Are you okay with that? When you have 2 polar curves and you're trying to identify the region, drawing your diagram large is going to pay dividends. Because when you draw it small, it's kind of hard to see things, right? Like just this little sliver of this area down here in pink that we need to subtract out. Okay, let's move on to the next one then. Because this one is same interval, but it's not always that case. Example 6. Find the area of the common interior of 3 cosine of theta and 1 plus cosine of theta. Step 1, identify the 2 curves. Let's color code them. Let's see. This one I'll use red. What can you tell me about 3 cosine of theta? It's another circle, off-centered, with what symmetry? X-axis. So again, if you point due east when theta is 0, cosine of 0 is 1 times 3 is 3. So it starts at 3, and then it's going to trace around like this, from 0 to pi halves, and then it's going to come around here, and it's going to finish up. This one traces out again from 0 to pi. And for some crazy reason, we go from Times New Roman to Comic Sans font for the word and. Yay! A little Comic Sans now and then does a body good. All right. Some people think Comic Sans is a humorous font, but sans actually means what? No. Without. So this is like without humor. This is like not funny at all. Okay. 1 plus cosine. What is that going to look like? 1 plus 1 cosine, I should say. Well, it's got 2 well, let's see. It's a cardioid actually. When the coefficient and the constant are the same. Let's just point due east. When theta is 0, cosine of 0 is 1, so I get 1 plus 1 is 2. So it starts right here at 2. And then at pi halves, we get 1. So it's coming in like this. At pi, I get 0. So it hits the pole, and then it's going to come back out and look like that. So I want the common interior. So the common interior is going to be inside both of them. So that's the first all-important step, is identify the region. If you have the wrong region, you're probably going to get the wrong number. Is that the right region? I just kind of shaded something. I don't know if that's right. Is that right? It's common. It's inside both, right? Good. Anything that's not that is either outside the green or outside the red. So that's inside both. Good. So notice again, we could use symmetry to our advantage. These both have what type of symmetry? X-axis. All right. So I know that if I want to start tracing the areas, I already sketched the cardioid by starting at theta equals 0. So I can start at 0, and as I trace out the areas on the cardioid, I can get most of the region, and I'll trace it from 0 up to that point of intersection. See right there? And of course, I'm going to double it. So if I can get it in the top, I'll just double to get the bottom. But now if I integrate from 0 to this point of intersection, if you were to draw this line through the point of intersection, that would be theta equals alpha. In this case, if I just integrate from 0 to alpha, I'm not getting too much, am I? I'm leaving off what? That little tiny sliver. That little sliver, which I could then pick up at alpha and go from alpha to 0 or pi halves. Remember, the red the red circle hits the first pole at pi halves. So I integrate the green curve from 0 to alpha, and then I'll switch curves and go on the red curve from alpha to pi halves. So instead of getting too much and having to subtract it, this is one where I need 2 separate integrals just to get the whole thing, because the curve switches, okay? So it's kind of like when we did rectangular area, you know, I had to set it up as 2 separate functions because the vertical slice, one of the curves changed. Same thing here. One of the curves changed. So let's find the points of intersection, which we're calling alpha here. So 3 cosine of theta equals 1 plus cosine of theta. So bring it across, and you get 2 cosine of theta equals 1. Cosine of theta equals a half. So if this ends up being like a no calculator question, it's going to have some nice unit circle ratios. So where's the first angle where cosine's a half? Pi thirds. Yeah, and if you kind of look at your diagram, you're kind of pointing up a little high, so around 60 degrees. Okay, so I think we're ready to set it up. The area is going to equal twice the integral. Again, we're using symmetry. I'm finding the top blue half. We have a symmetrical one down below. So twice. And then I have 1/2 the integral of the green curve. So that's from 0 to pi thirds of r squared d theta. And my r for the green curve is the cardioid, right? So it's the 1 plus cosine of theta. And then d theta closes up that integral. And then plus or minus? Plus, yeah, plus. Now I need to get the other piece, plus 1/2 the integral from pi thirds to pi halves. Just a tiny little sliver of r squared d theta. And in that case, r is going to be the 3 cosine of theta. So there is the setup. And of course now, whether it's a multiple choice question where we're identifying the integral or we have to integrate it by hand, we can simplify. So we can distribute the 1/2, which is nice. Can I combine these into one integral? No, because these are on separate intervals of integration. So the first one, if we had to do it without a calculator, we would have to square, multiply, double square, use the power reducing identity like we saw in number 1. A lot of work involved. The next one here, at least with the 1/2 gone after we distribute the 2, I can simplify that and call that plus 9 out front. Integral from pi thirds to pi halves of cosine squared theta d theta. And so now, even if it were a calculator question, you would probably want to simplify to this point. So now you have something you could type in. And what's that? Remember that, again, your calculator, the way you type in cosine squared of theta, when you hit cosine, it opens. You're in polar mode probably, so you hit x and you get theta. You square it like that. Okay? When you square it after you close the angle, it acknowledges it as the function squared. All right, so I think we'll stop right there today. Tomorrow we'll do example 7 and maybe one from the worksheet, which will be like free response type questions. And then the second half of class tomorrow we'll start chapter 9, sequences. Okay, sequences and then series, and then we're done. So this Saturday, if you're competing at UIL Academics, good luck. If not, I'll be in here at 7:30. If you want to come, I'll probably take a poll on Friday to see how many people will make it. If no one raises their hand, I don't think I'll come in at 7:30 and teach to an empty room. Although that wouldn't be the first time that happens. I did that like through Wednesday on spring break, and then I realized, oh crap, it's spring break. Yeah. Okay. Have a good rest of the day.